Hello everyone, how is it going there? Welcome back to this course on discrete mathematics, and today we are going to see about the set theory actually. So in set theory we are going to look at different parts, and this first part we are going to see some basics of set theory, and the whole sections of set, most of that you have already studied in your high school, and we will see brief review of that in the part 1 and part 2, and later on the part 3 sections we see some practical aspects of set and some complications that are involved and what are the advantages of having set in itself. Well, talking about set theory itself, it has a huge research area where people are still working on defining and proving and disproving many aspects for set. Later on we will see some topics on functions and relations. So just keep this in mind when we talk about functions and relations, because we will see some similarities as well as some differences between sets, functions as well as relations. Moreover, the set has been done, the research on set has been done for long ages. We can go back even before Christ, people used to form sets. Let's define it first and then let's talk about it more. What is a set? Well, a set is a group of objects. So now you can think about how this can be used in various areas and how this has been used in the past as well. For example, people in a class like Alice, Bob, Chris, they can be a part of a set, or classes offered by a department, CS 101, CS 102, CS 103 and so on. Yes, this group can form a set. Colors of a rainbow, yes, red, orange, yellow, green, blue, purple, they form a set. Why not? States of matter, solid, liquid, gas, plasma, yeah, they form a set. Can you think of something else? Yeah, there is more to it. States in the US, Alabama, Alaska, Virginia. Sets can contain non-related elements like 3, A, red, Virginia. You can see these are numerics, characters, color and a state has been there. They are not related. So although a set contains almost everything that we have seen here, as well as you can still imagine looking at different objects being part of the set, most often here in this lecture we are going to discuss about the set of numbers, all different numbers. All positive numbers less than or equal to 5 can be written as a set of 1, 2, 3, 4, 5. In the same fashion, a few selected real numbers are given here: 2.1, pi, 0, minus 6.32, exponential this e is there. So, well, let's see more about this properties of set. In this set, order does not matter. The way in which you place these objects does not matter. So that's one of the important property here. So we often write them in order because it is easier for humans to understand it. Later we will see some points on the so-called ordered tuples, where we will consider some specific areas in which we might need ordered pairs of set, but in general the main property of set is that it does not need to be in the order. Yes, order does not matter. For example, a set of 1, 2, 3, 4, 5 is equivalent to 3, 5, 2, 4, 1. Right, the order does not matter there. Sets are noted with curly braces. Yes, we just often use the curl braces or curly brackets to indicate the set of elements that contained in a set. We have few more properties. Sets do not have duplicate elements. Yes, consider a set of vowels in the alphabet. Suppose if you want to express a set in like A, E, I, O, U, this doesn't make any sense because set does not have a duplicate element. This is just equal to A, E, I, O, U. So what we really want is A, E, I, O, U. So that's it. We don't have duplicate elements in the set. So when you consider the list of student in this class, again it does not make sense to list somebody twice, right? Exactly. So keeping these properties in mind, later on we will relate this with that of functions and relations. So you will see their properties vary a little bit. Note that a list is like a set, but order does matter and duplicate elements are allowed. So we are not going to discuss about the lists, where rather we are going to just discuss about the set here. Right. Specifying a set. How do we specify a set? Sets are usually represented by a capital letters. Yeah. Set A, set B, set S. All sets are just represented by means of a capital letter. And the elements in the set usually represented by means of italic lowercase letters. As you can see here, A, X, Y, so on. They are in the lowercase. Yes. The easiest way to express a set with a list of elements in it, as you can see here, A equals the capital A that represents the set, that's equals to the curl, within the curl braces you have 1, 2, 3, 4, 5, the 5 elements. So this set A has 5 elements, they are 1, 2, 3, 4, 5. Yes, now you can recall what you have studied in your high school or even in your junior high school about sets. Yes, sometimes and often times if you are playing with quite large set or infinite set, it's not easy to specify or to represent all elements in the set, especially manually considering all the elements. It's not feasible for us to represent and to write down all the elements. So we'll see in short, we can use certain forms, certain limits to express it. We'll come back to it soon. Specifying a set further involves, you can still use ellipses, but we should be of caution. Of course, it's not recommended to use ellipses because at times it may be confusing. For example, say you have a set C that has 3, 5, 7. What does it represent? It looks like this is going to be an infinite set, but what comes next? Well, you might wonder, there are two options that we have. If the set is all odd integers greater than 2, then the next number to be is 9. But what if the set is all prime numbers greater than 2? Then the next number is going to be 11. Yes, so that's why if we are defining things with ellipses, or if we are defining certain sets that looks like this finite nature, infinite nature, in that case you can use the set builder notations. Yes, as I told you in the previous slide, we can use certain ways to express the limits or the conditions to express the elements status in a set. For example, here D, the set D equals set of all x such that x is prime and x is greater than 2. Here the set E has x for all values of x such that x is odd and x is greater than 2. Yes, the vertical bar here indicates such that. Yes, so you can see we can try to express things using the set builder notations, and these notations are also useful for you to keep this in mind later on in your career of computer science and engineering. We will be coming across various notations in different areas, for example even in cryptographies or in artificial intelligence or machine learning. Wherever you are learning a different area or different things that are related to computer science and engineering, in other words computing elements, you might come across certain notions that you have to understand. Well, these are very basic notions. For example, this set D, as I just said, set D in English you can read it as all elements x such that x is prime and x is greater than 2. Let's give more thought on this properties of set. A set is said to contain the various members or elements that make up the set. Well, we know that if an element A is a member of a set S, we used to say with the notion A with kind of, it looks like E, this symbol represents that element of, A is the element of S. So here we know that 4 is the element of the set 1, 2, 3, 4. Yes, if an element is not a member of a set S, we can use the notion here. As you can see, A is not an element of S. Just a slash mark or a cut, you just make sure that it's not. Well, then we'll see an example here. 7, yeah, you can see 7 is not an element of the set 1, 2, 3, 4. And Virginia is not an element of the set 1, 2, 3, 4. Yes, you can think many more examples. Let's see here. We have a set of natural numbers, that's n equals 0, 1, 2 and so on, a set of natural numbers, and z is a set of integers which has both positive and negative integers, yes, -2, 1, 0, 1, it goes on, and z plus indicates a set of positive integers, or in other words kind of whole numbers starting from 1 onwards, 1, 2, 3, so on. So at times people use different terms to express it. Note that people disagree on the exact definition of whole numbers and natural numbers. So here is another way of expressing q equals p by q, such that p is an element of z and q is an element of z, where q is not equal to 0. Can you get the point? And it's said that it's a set of rational numbers, right? So p and q, they are part of the set of integers. It can be either positive or negative integers, and q cannot be 0, so that we have a proper rational numbers there as a set for the set q. Any number that can be expressed as fraction of 2 integers, yeah, that's where we call as rational numbers, where the bottom one is not 0, and R is a set of real numbers. So these are the terms we are going to use in our lectures, because I have found some literatures and some professors, they like to use I for the set of integers, but here for example we are using z, just for you to see the difference. So it doesn't have big impact in representing, but the main idea is to get the grasp of the concept that we are dealing with. Universal set. what is a universal set? A universal set, the set of all elements or the universe from which a given set is drawn. So we represent by this block letter U, capital U. For example, here for the set -2, comma 0.4 and comma 2 here. So these 3 digits are taken from the universe of real numbers, where the U would be the real numbers. A set 0, 1, 2, U could be the natural numbers 0 and up, or it can be integers, it can be rational numbers or real numbers depending upon the context, right. So always remember that we should know what is the universe, so that we can apply this various terms for the set. We will talk more on this universe now. For the set of students in the class, U would be all the students in the university. So among all the students in the university, we have a set of students in our class. So maybe say 60 students in our class, but we have like 30,000 students in the university. Yeah, the university is the universe, and you have a set drawn out of the university, that is the students in the class. Even for that matter, you can consider the universe as all the people in the city, all the people in the country, all the people in the world. Yes, your universe is becoming larger, but you can draw out the set from it. For the set of vowels of the alphabet, the universe would be letters, all the alphabets, letters of the alphabets. For example, you can say A to Z is the universe, and you are going to extract, or you are going to take a set out of this alphabets A to Z, and that is going to be your vowels A, E, I, O, U. To differentiate the universal set, that is represented by capital U, blocked capital U, from U, which is the operation, it is called union operations. We will just we'll discuss that in this course, probably in the next lecture of this series of set. The universal set is written in different font. I can see here it is in bold and italics. Venn diagram. Yeah, Venn diagram has a great impact, and it can help us to easily represent the whole set and the difference between one set and another set. Yeah, you can see here the universe there is the whole rectangular box, that space is the universe, and the set S is within the universe. For example, you can consider the universe as a set of all students in the university, and S is the students in the class. As the box represents the universal set, circle represents the set. Consider set S, which is the set of all vowels in the alphabet. You could see here the universe has all the alphabets A to Z, but S contains only A, E, I, O, U from that universe. So S has the set of alphabets. The individual elements are usually not written in Venn diagrams, so we just represents a set as such, not the individual elements in the set. Set of sets. Sets can contain other sets. For example, S equals, we have set 1, set 2, set 3, yes, and you can see T is a set that contains 3 elements, and again these elements are part of a set represented as a set itself, because things, whatever elements that is within the curly braces, we call it as set, and there it is. The sets are also part of the elements of another set here, and here we have seen there is other elements. So V has only 3 elements. You can see how the sets within a set contains and be part of the elements there. And note that 1 is not equal to a 1 in a set. or set within a set which has 1, or set within a set within a set which has the element 1. They are not equal or they are not same. Yes, they are different. Empty set. If a set has 0 elements, it is called empty set or null set. So if we represent by means of this 0, or in other words we can call O and slashed shine of this. So it has a 0 element or an empty set, and often we just simply say it as within curly braces with nothing placed inside. And if you get confused about the empty set, just try to replace this this symbol that we have, the circular slash, by means of just empty curly braces. As the empty set is a set, it can be an element of other sets. We will see how it is. For example, here the first part is the empty set, which is part of this set, and 1, 2, 3 and x or other elements. Yes, this is a valid set. More on empty set, we can see this empty, the element, we have the empty set on the left hand side which is not equal to the empty set which is part of the element of another set. They are different. Just in the case of 1 is not equal to a part of a set which contains 1. The first is 0, the first set is 0 element, the second set is set of 1 element, that has 1 element being the empty set. So it is better to replace empty set with the curly braces, and you can get that. Remember that the empty set itself is not equal to the empty set that contains another empty set as an element. Just is a piece of cautious things that we have to understand. It is easy to see that they are not equal that way, and we see two sets are equal if they have the same elements. So that is what we call as equality. 1, 2, 3, 4, 5 is same as 5, 4, 3, 2, 1, and as we have seen before, the order does not matter. Rather we can see here 1, 2, 3, 2, 4, 3, 2, 1 is equal to 4, 3, 2, 1, because you can see we do not worry about the duplicate elements. Duplicate elements does not matter, but all the elements in the left hand side is equal to the elements in the right hand side. Two sets are not equal if they do not have the same elements. As we can see here, 1, 2, 3, 4, 5 is not equal to 1, 2, 3, 4, and we will going to shift our gears to the subsets. If all elements of a set S are also elements of set T, then S is a subset of T. Remember this definition. With this thought we can move ahead. For example, if S is 2, 4, 6 and T is 1, 2, 3, 4, 5, 6, 7, then S is a subset of T, and this is specified as S is kind of you could say less than or equal to, kind of less than or equal to sign we have here. So this is a symbol used to represent that S is a subset of T. Or we can say that 2, 4, 6 is a subset of 1, 2, 3, 4, 5, 6, 7, because these 2, 4, 6 elements are already contained in this set that has 1, 2, 3, 4, 5, 6, 7. So that is the definition. All the elements of a set S are also element of set T. So if S is not a subset of T, it is written such as S is, just you got to slash it off, not a subset of T. For example, 1 to 8 is not a subset of 1, 2, 3, 4, 5, 6, 7, because we do not have the element 8. And you have here subset, the part 2 here. Note that any set is a subset of itself. Given a set S 2, 4, 6, since all element of S or element of S, S is a subset of itself. Let us see what it is. This is kind of like saying 5 is less than or equal to 5. Yeah. Thus S is a subset of S. Empty set is a subset of all sets including itself. though it has no elements, it is a part of all sets. Recall that all sets are subset of themselves. Yes, these are important property of subsets. All sets are subsets of the universal set. Yeah, that's going to be true because they are contained in the universal set. So here's a kind of horrible way to define a subset. For all possible values of x, meaning for all possible elements of a set, if x is an element of A, then x is an element of B. We are using the quantifiers and implication operators to define it. Still, you see, we are trying to link it off the sets and the things that we have learned earlier. Proper subset. If S is a subset of T and S is not equal to T, then S is a proper subset of T. So which means that if T is 0, 1, 2, 3, 4, 5 and S is 1, 2, 3, S is not equal to T and S is a subset of T. Here in fact T is greater than, it has more elements than that of S. So we could say that S is a subset of T. In other words, S is less than T. So you could say that all sets are proper sets of the universal set. That could be applied as well. So let R equals 0, 1, 2, 3, 4, 5. R is equal to T and thus is a subset of T, but it is not a proper subset because here they are equal. According to the definition, they should not be equal. So that's why we write R is less than or equal to T, but R is not a proper subset. Let Q equals 4, 5, 6 and Q is neither a subset or T nor a proper subset of T. You could see here the element 6 in the set Q is not found in T. So it cannot be a subset or it cannot be a proper subset. The difference between subset and a proper subset is like difference between less than or equal to and less than. The empty set is a proper subset of all sets other than the empty set. As it is equal to the empty set, we could say it is a subset of empty set itself, but it is not a proper subset of the empty set. So you can think of some more examples and see how it works out. For example, if let A equals, let the set A equals 1, it has one element, and say B equals number 1 as an element and a set that has 1. So the question is A a subset of B? What do you think? Is A a subset of B? From the things that we have learned, A has only one element, here namely the symbol 1 is used, and this element is also one element of the set B that fits the definition of a subset. Hence every element of A is in B. So we can say that A is a subset of B. Okay. So if A is a subset of B, now the question is A a proper subset? Is A a proper subset of B? So here is the thing for us to just review it. We can see here B has two distinct elements. What are they? They have a symbol 1 and a set that contains only one element, that is 1. Since we can see that 1 is not equal to the set which contains one element, and set that has one element is not a part of the set A, only it has been in the set B. So there is an element of B that is not an element of A, hence we can say that A is a proper subset of B. Yeah, we could simply also say that it is a subset of B and it is also a proper subset of B. So that is the simple argument that we have been using it to define it. So today we have just seen various properties, various elements of sets, and we have seen what is a subset as well. Before we go on to the greater application of set, we have to still follow some of the identities and some of the laws that are found in sets. So we will see that in our next part of sets. So until then, goodbye.